Hi, my name is Chris Collier. I'm presenting some work that the team and I have done on identifying hearing difficulty moments in conversational audio. We're a group out of Google, and this is a collaboration with the AFHI, the Australian Future Hearing Initiative, which focuses on new applications of AI and machine learning to develop research to improve technology for the hearing impaired or hearing aid technologies. The particular focus is on customized hearing healthcare. So that is devices that can provide um, specially customized functionality for the particulars of the hearing loss of an individual. Why do we want to identify hearing difficulty moments? Well, 1.5 billion people are affected by hearing loss. For 430 million of these, the loss is severe and has negative effects on the quality of life, both physical and mental. And the cost is around $1 trillion US dollars annually in treatment and lost productivity. So, what did we do? We studied classification of um, events in conversation through audio in which one of the conversants is having trouble hearing or understanding. We used some pretty standard data sets for this study. Um, we had 1,200 long conversations from the Switchboard Dialogue Act Corpus, or SWDA, and the Meeting Recorder Dialogue Act Corpus, or MRDA. These are data sets that have been around quite a while and have been heavily labeled over time, human labeled with annotations that are basically a standard set of Dialogue Act labels, meaning each utterance in the conversation is labeled with a type of utterance in the conversation. It could be a confirmation or a question or something like that. There is a label for something called signal no understanding, which means that the speaker is signaling that they do not understand. These utterances are relatively rare. They represent less than 10% of the entire data set. Um, we took the signal no understanding utterances and manually refined them because there are a variety of different situations in which someone might not understand, and we um, refined them down to examples where a person seemed to actually be not hearing properly and not understanding what was being said. Um, and so this turned into 298 examples out of the 1,200 conversations. We defined hearing difficulty moments as, as I said, one of these labeled signal no understanding utterances, and we included 4 seconds of context audio before the utterance, um, and the event had to occur for at least zero point 0.4 seconds. For the negative cases, of course, there were far more of those than there were the positives, and we randomly sampled those and ensured that they were not overlapping with the positive samples. Approaches we took to the classification, we took a baseline using an ASR hot word heuristic. Explain that in a minute. We fine-tuned a wave to vec model. We ASR prompted a text language model, and we prompted an audio language model, the audio. And we LoRa fine-tuned also an audio language model. The baseline heuristic, uh, we generated that with a two-step process. The first was using chirp2 to transcribe the audio. And then we used a simple dictionary lookup, basically, with hearing difficulty words such as what, pardon, sorry, to determine if there were any indication of hearing difficulty in the language. For the wave to vec fine-tune model, we replaced the final layer with a standard 2-layer DNN classification head. And then we trained the entire model using a learning rate of 1 times 10 to the negative fifth. We froze the model's trunk and trained only the new head then. And that had significantly lower performance than training all of the weights. The prompted audio language model. This is a multimodal Gemini 1.5 Pro. We adapted the P and N tokens as our predicted classes and prompted with detailed instructions on analyzing the audio for signal classification. We made sure to detail both semantic and non-semantic information about the hearing difficulty moments. And we used zero shot and few shot prompts and compared those. And we preserved an equal number of positive and negative examples in the prompting. And then we took the softmax probability for the P token as the predictive signal. This graphic shows on the left zero shot and on the right 50 shot prompting performance. It's a time series graphic where the red is the actual ground truth signal of no understanding utterance, and the blue is the predicted. And you can see on the left, the blue is much more, the zero shot is much more noisy than the 50 shot, indicating that the examples make quite a difference in the performance of the classification. For the LoRa fine-tuned model, LoRa is a low-rank adaptation technique, and it's used to efficiently adapt large models to specific tasks. It trains a very small set of the model, changes the weights only in a very small part, but still can perform quite well. We fine-tuned a Gemini Flash model on our training examples using this technique. And the results from these different approaches, the ASR hot word baseline, F1 score of 0.39, and then wave to vec, as you can see, just getting away from the baseline was a significant improvement in performance. And zero shot prompting of the audio Gemini model, F1 at 0.75, and then up to 0.85 for two shot. So showing that examples make quite a difference there. And 10 shot 0.87. And for the LoRa fine-tune model, we were about, this has 0.95. I think it was more closer to 9.3. 0.93, we need an asterisk on that because those results are not completely finalized here, but they are, they will be very close to that. Precision recall curves for the different shot prompted model experiments. And as you can see, as we add numbers of examples, the performance increases significantly. Not surprising. So in conclusion, we've shown that you can definitely leverage audio language models for audio classification of utterance, of this type of utterance. And the involves a level of audio reasoning that goes beyond ASR. We've established this task that it's possible to achieve quite good results with few shot prompting and fine-tuning approaches. And the results exceeded the performance that was achieved by fine-tuning wave to vec. So additional takeaways and future work. This work does not take into account real-world latency requirements that you would need from something such as a commercial product where you would want to be predicting non-understanding utterances. So deploying these models onto edge devices isn't possible. We use very large models. So the next challenge, or one next challenge, is distilling the knowledge down to smaller models that could run on smaller hardware. We'd want to do this because devices that might be helping a user with hearing, so as a worn device that is processing audio to help the user hear, typically use battery, and we don't want to have them on all the time using battery, and detecting not understanding would allow the device to be only turned on when it's needed. This is just one example of when this kind of classification could be useful for assistive hearing devices. And that's it. Thank you.